Hello, I'm Rick Elwell from LP Management. I'm the Senior Electrical Safety Instructor and Technical Consultant for LP Management. What we do is we help clients develop and maintain top-notch safety programs in compliance with OSHA by helping them develop policies, audits and surveillances for safety, and do a variety of training, which is our core is safety training, electrical safety, lockout, tagout, arc flash, and we also include a variety of technical training such as electrical troubleshooting, hands-on. And what prides us is the fact is we bring electrical equipment into the classroom to allow reinforcement of the information that was presented during the day in PowerPoint format so that we can get hands-on experience with the equipment. Today we're going to be talking about proper selection of personal protective equipment and then complete a three-phase AC system zero energy verification check, which is a term commonly used for live dead live. And we'll explain it as we progress. So why is this important as far as safety is concerned for those who are conducting maintenance? Because most people are shocked or electrocuted or possibly killed on equipment that they believe or assume to be de-energized. Because one, they may not know that they should be checking de-energized, and if they do, they may not have the proper techniques to do it properly and effectively. Electricity is no joke. You can't see it and you can't hear it, and by the time you feel it, it's often too late. Okay, and it's not just electrocution you have to worry about. During switching and during a live dead live process as well, there's always a possibility of an arc flash. So there are things that you need to do to protect yourself. One thing that we like to train is not only why you're doing it and why it's a requirement. In this case, doing a live dead live is a requirement of OSHA. OSHA lockout tagout is Article 147 of General Industry, and it's also subpart S, which is Article 333, which talks about the live dead live process and verifying electrical equipment is de-energized. So how could you find power when you don't expect it? Sometimes switches fail. If you operate a switch and the switch is internal here, and one of the three phases happens not to open, maybe somebody closed it into a direct short previously, and one of the three phases still has voltage passing through it. Another possibility is there's modifications that you may not be aware of, that they may not be on electrical diagrams or prints, and those are probably what you're going to be utilizing to develop your lockout tagout isolation, and you may have unfortunately missed something. And then also mistakes happen. People are human. If the person who's operating the switch, unfortunately, maybe they had a bad day, they got the wrong circuit, they should have opened circuit breaker number 3 on the panel board. Instead, they got circuit breaker number 5. It was a mistake, which would be caught when you do a live dead live. Other things that I've seen is mislabeling, particularly on new installations. And also circuits that have been installed incorrectly, meaning that the power source is connected to the wrong circuit breaker. So those are some of the possibilities that you have to be aware of when you're doing something as simple as a single source verification. And so we'll talk about that. So most of the work that you're probably going to be doing is on de-energized equipment, which you're going to be locking out and verifying de-energized. That's one of the primary and most important steps of the lockout tagout process when you're dealing with electrical equipment. The other steps that you may see here are isolation, how to safely isolate this, how to safely switch to make sure you're doing it just in case something were to blow up. Anytime you make and break electrical connections, there is a possibility. Also, how to test and apply locks. That's not part of this presentation because we don't have a lot of time for that, but it is an important aspect of lockout tagout process. First thing, so we'll go ahead and get started on this, how to actually do a correct live dead live or verification. The first part in process is to make sure your meter is adequate and is going to protect you if it were to fail, and then selecting the right meter so it does not fail. So I need to have the right rated meter. Okay, and it's not just the voltage rating that you have to be concerned about. This is a 1000 volt category 3 meter. This is a 208 volt controller, which is 1000 volts is obviously greater than 208, so voltage wise it's able to protect me. But what's also equally important is the category of the meter. okay? And we'll talk about that in the subsequent slide here. Inspect the meter and instrument and the test leads for errors or faults, okay? So if I have a open lead and I have the insulation is broken, whatever I apply it to could potentially make contact with me, and then I'm the source and current flows through it. So that's one aspect. The other is crimped leads can indicate false readings. So do a appropriate check on those leads to make sure that they are good to go, and also that they are rated appropriately for the meter, because you can have a low rated meter leads, which may be a category 2 lead in a category 3 meter, and it's not going to protect you because the insulation is not appropriate. Also, the finger guards. These finger guards are required to be in place so that when you're doing your tests, you don't slide your fingers on to make contact with potentially live equipment. And then if you do find damage, which after you do a visual check on it, on all your equipment, make sure that you do not use it if you find damage to it and you get a different meter. That's very, very important. So let's go back to category. Category 3 is 3-phase industrial AC and 277 volt lighting. So a category 3 meter is capable of withstanding either 6,000 or 8,000 volt surges, and a category 2, which is just for shop equipment, and a category 1 for electronics, may not be. So bringing that into your facility and then doing a live dead live would not be a safe thing to do. So that's really important. The other thing is yes, proximity meters exist, which are basically they sense electronic fields, and they indicate. On low voltage systems, they can be inaccurate or inadequate fields, and they may give you false readings. Medium voltage equipment may be used as the sole means to check something live, dead live, but what you want to use is a contact meter like I have in my hand. One other process of the procedures is to establish boundaries. Okay, what that does is when you're working in here doing the process of live, dead live, and you're verifying the equipment is zero energy, your attention is here, not out here. So you want to make sure you protect yourself by setting up boundary controls, which again we'll talk about here shortly. Ensure that proper PPE is worn. Personal protective equipment is important. What people assume that because I tagged it out, that means there's no voltage. You have to assume it's energized until you've proven it. In that regard, you have to take all precautions as if you're working on energized equipment, because at that point you don't know. Until that last live test is done, you have to make sure you protect yourself. So we're going to talk about that. That's one aspect of today I want to get through to make sure you understand the process of selecting the appropriate levels of personal protective equipment, not only for shock but also for arc flash, which is required anytime you open a piece of equipment that has potentially live or live terminals or parts. The process we're going to talk about when you put a meter on before you touch it is a test before touch. So on the aspect of boundary controls, now I don't have the boundaries established here, but they should be encompassing both the shock protection and the arc flash boundary protection zone. Okay, on the label you see on the slide is a typical arc flash label. It might be different from one engineering firm to another as far as their formatting, but the general locations of this information is pretty much similar from one location to another. So if you look at the label, the arc flash boundary set at the onset of second degree burns. So it will vary based on the initial start. In this case, at the work zone, it was 1.7 cals per centimeter squared. And then, so beyond that, or inside that, was the arc flash boundary. And that's to protect the people that aren't protected, aren't in the same level of personal protective equipment to protect themselves from a blast. The other boundary of concern is the shock protection boundary, okay, which is a limit approach boundary. Generally on low voltage equipment, that's going to be 3.5 feet, okay? And that's to protect the people from making contact, who aren't in the same level of insulation protection, and also protect you from being pushed into the equipment. Because again, your attention is elsewhere. When you set up the boundaries, danger is a key word to indicate to an individual who's passing by that there is a danger that exists that could potentially severely injure themselves or cause death. And so they should not pass. Caution means to identify the hazards and proceed with caution. So that's why danger tape is probably the most appropriate if you're using that, or some sort of danger signs. Arc flash selection guidance. Some of the information I'm going to be putting out is straight out of OSHA and also NFPA 70E. Okay? NFPA 70E is a standard for electrical safety in the workplace. We do recommend that all facilities purchase a copy of it because it has the best practices to make sure that you maintain your safety, so when you're doing hazardous equipment type work that you're protected. In NFPA 70E, there's two methods to select the level of PPE. One is using the incident energy analysis method. That can either be conducted using the annexes or the appendix in the back of the NFPA 70E and calculate those using the calculations in the appropriate section, but also can be used by or abided by looking at the arc flash labels if you had an arc flash analysis. The other aspect to that is when you don't have a label, an arc flash label, and it doesn't tell you exactly what to wear and then where do you set your boundaries. So that you have to go to NFPA 70E and look at their tables. Now I don't have a copy of those tables because it's proprietary information, but those tables basically refer you to the type of task you're doing, and then you analyze it based on that task and then several parameters. If what you're doing is unsafe, and then if you need to utilize personal protective equipment. And then it refers to another table that based on that, then you determine what category of personal protective equipment that you need to wear, and it'll tell you specifically what's part of that category. So that's NFPA 70E table. So that's the other method that would be available to you. So if you were looking at a label and labels were installed like you have here, to get the important information that you need to know the cals per centimeter squared. Now that's based on the worst case, 3-phase short across all 3 phases in the worst case condition. So I can select my personal protective equipment based on that. For example, that was 1.7 cals. An 8 cal suit is greater than 1.7, so this suit will be able to protect me from the thermal energies involved with an arc blast. The other aspect is glove selection is based on the nominal voltage value. Okay? On a label, it's going to list the highest voltage value and the type of voltage that you're going to be potentially exposed to. In this case, it's 208, and if I wore a category 0 gloves, like I have right here, it would protect me from shock. Okay, so we'll walk through the actual personal protective equipment, each article of clothing or article in the ensemble that's necessary to protect you and why. Okay, as far as the tests, now as I'm going through here, I'm going to walk through. Okay, you have to first find out a known live source. Typically an outlet, doesn't have to be, but I want to make sure my meter is actually working as I expected. Now this is all after your visual verification checks. Make sure that your meter is integrity is adequate to use. Select the right voltage selection. In this case, I'm only dealing with AC. If you were dealing with DC, not only would you have to check on an AC source, you'd have to check on a DC source, like a UPS system. It would have to be both AC and DC. So in this case, which is just an AC source, okay? In the slide, he's using an outlet. For me, it doesn't necessarily have to be. If you have a known voltage source in your work area, now I'm not going to go ahead and, actually what I'll do is I'll go ahead and keep these on. I'll just show you what needs to be, what you need to put on in order to protect yourself. If you look at NFPA 70E and you look at the back of the tables, it'll say you based on the incident energy level, worst case of the equipment, and after the analysis has been performed, you'd go ahead and use that as a starting point. For me right here is 0.09 cals per centimeter squared, which is a relatively low value. In the back tables, there is also a table that will aid to determine if what articles of clothing are necessary for that. So anything less than 1.2 cals, I would need rubber safety gloves. Okay, just a real quick check. I've seen a lot of various methods on to make sure that you have to do an air test and you have to do inspection. That's an OSHA requirement. It's required once per shift, per person, and if you transfer responsibility, it has to be done again, and it's only one time unless you suspect damage may have occurred. I've seen the blow method. I've seen the flippy method, and in all cases, you don't trap enough air to do an adequate air test. So what I train is turn the glove perpendicular, roll the glove, crimp it using a horseshoe method is what I call, hold it, and then hold it up to your face where it's real sensitive. So not only are you going to hear it, but you're also going to feel a leak if a leak actually exists. So do the front and the back. So you're not just looking for holes, you're looking for signs of degradation, oil impregnation, stuff like that. And then look to make sure the cuff is intact as well and there are no holes, because you've rolled that up during your previous air test. And then make sure that it's properly tested. Okay, every 6 months they should be sent out to a testing laboratory to go ahead and do a high voltage test on it to verify that the glove isn't damaged integrity that you can't find during a visual inspection. So I'd go ahead and put those gloves on. Always will you be putting a pair of leather gauntlets on. And the reason for that is you want to protect your hands from an arc blast. Say it started out at 1.9 at the work area. Now that work area is going to be 19 or 18 inches. I have to maintain my whole body, which is my head and my torso, that 18 inches. Now my hands are maybe within 1 inch when I'm doing a dead live test. So that exponentially increases. So you got to protect their fingertips, not only from sharp ends like a fluke lead, okay, but also from the blast itself. Okay. The next thing I would have to wear is hearing protection. Okay, which I'm not going to put on because just for training purposes, just so I could show you that obviously you need it. I also need to have my face shield, okay? And this is, like I said, the minimum for this particular scenario. The face shield's intact. I do a quick compression test on my helmet. This helmet is either a Class E or Class G helmet. And then the last thing is a pair of safety glasses or safety goggles over the top, underneath, so that you protect your eyes from shrapnel damage. Okay, so those are some of the things that you would have to have on. So now that I've shown that, I'm going to go ahead and take them off. Just like I said, normally we'd make sure that they were on while we're doing this test, but I just wanted to make sure everyone can see the actual application of the leads. So I don't want to obscure this test so you can actually get an idea of where we're going. So back to the live dead live. The first thing is a live test. Now since this is my isolation point, when I'm doing a lockout tag out, I can determine that, not have to go upstream if I'm working somewhere outside of this controller. Okay, somewhere down, like for example, motor replacement, which is outside the controller. If I'm working anywhere in here, since there's not a protective guard there and there's a possibility of contact, my isolation would be upstream. But since my work scope is outside this controller, I can use this as my isolation point, and I know I have a known live source here. Okay, so all I have to do is verify that my meter indicates the way I expected it to. Okay, I should get a reading, in this case 208 volts. Okay, the next thing is, which I'll go ahead and progress through the slides, is you got to find an appropriate ground point. Okay, anytime you're in an enclosure like this, you're going to have a green or a green and yellow lead that you're going to have a contact or a point right there, which is a good ground point. Don't use metal, okay, which is painted metal normally. Don't use the door, I've seen that, because this is not a good continuity from the hinges on. And then paint and also rust, even if there's no paint in place, can add reduced continuity. You want to have the lowest resistance path, a good zero reference point when you're doing these tests. Okay, so the next thing I'm going to demonstrate is what I term 6-point checks, which is face to face, face to ground. That's going to verify that we have no primary power coming into this controller or this control unit. So I'm measuring phase A to B, or L1 to L2, L1 to L3, and then L2 to L3. Okay, that's face to face. Okay. The next check is to ground. So I want to check all 3 phases of ground. And there's a reason for that. If I just verified all 3 phases together, or all 3 points, and I walked away, there could actually be power in there. For training, I have a switch here that would simulate a stuck phase here And in fact, we'll show you the schematic. If you go through the transformer, the voltage at that point through the transformer is the same as that point. So if I'm doing a phase-to-phase check, I'm checking a difference in potential. Since it's the same phase, same voltage, you're not going to get a difference in potential. So the phase to ground points is really important in this case. I check A to ground, I verify 0 volts, B to ground, get the meter. 0 volts, and C to ground at 0 volts. Just for understanding, this is not energized. I don't even have it connected to the wall. I just wanted to do this for presentation purposes, so that way everyone gets an idea of how to do this properly, because it's really important. Okay, so I just wanted to show you the schematic that would represent the inside of this controller. Okay, A on the slide represents the primary power. That's the main power coming in. And in most cases, control power is transformed down off main power, as you can see here. Okay, but there's other things that you may have to be concerned about. And if you don't verify, you may not know exists. And that's, for example, remote indicating power to indicate that that motor's running or stopped has to have power coming from an external source to an auxiliary contact on this main contactor and then back out. So you're going to have another potential voltage source there. Okay, so you have to know that about the equipment before you go ahead and start working it. But a good thing to do is to leave a lead on ground and then check every point, potential point, including potential backfeed from the motor and the auxiliary contacts, to make sure that there's no other sources of power coming in. Why off the motor coming back to the controller? Because if there is any differential pressure, and if that fan, the motor is supplying a fan, it could be spinning, and if there's residual magnetism, the requirement for generator action exists, and it could push power back into the system. Okay, so that would be considered real voltage. It might be a small amount of voltage, but that's something you have to be concerned about. Okay, if you get voltage that's verified not magnetically induced, first what you'd want to do is stop, control, close up your work, inform supervision, and then verify or try to investigate the reason. If it was because this breaker failed, okay, we can still conduct this maintenance by isolating upstream. So we have to shift our isolation points. If we found voltage because we got the wrong breaker, okay, it was your accident, your fault, you go back, you've identified, hey, I should have been on circuit breaker number 3, but I got circuit breaker number 5. Well, that can be adjusted as well, but you want to place your work area in a safe condition before you do that. Now, if you don't have voltage, and the reason why I left this open is the last thing you want to do, and this is really, really important. This is why they call it live, dead, live, is I want to verify, again, on a known live source. Now, that can only be one check, just to verify that the meter deflects as you would expect. And if this was energized, I would get 208 volts on my meter. Why is that important? Well, if I use my meter to check it de-energized, in the process of doing so, it failed internally. Okay, every subsequent reading would be wrong. Okay, the other reason is every meter, in this case, this meter has a hold button here, has a hold button to lock in a reading, so you can document it or whatever the reasons. This will indicate to you that a warning by giving me a beep. Some meters don't do that. Okay, so if that's on hold and it's held on 0 volts, every reading thereafter is going to be 0 volts. So that's something you're not going to catch until you do the last live check. Okay, and I've seen it over and over again that people accidentally hit that button. It's easier to do when you have your gloves on with the leather gauntlets. And basically that's it. It's a simple process. If done correctly, is going to save you from being electrocuted, worst case, shocked. Just make sure you can work it without the personal protective equipment. So I hope everybody learned something today. And I'm glad I had the opportunity that IMA gave me to get in front of you today, because the process, in my opinion, is very, very important on how you do it and how you do it correctly. I encourage, again, everyone, all facilities, to get a copy of NFPA 70E. And then that way you can go ahead, if you don't have an arc flash analysis, or if you do, and some of the equipment is not included in that, which often is the case, that at least you know how to select the appropriate level of PPE based on the scope and the type of equipment and the tasks you're actually performing. I also encourage you to go to our website. We have a lot of variety of various ranges of training, again, which are way bigger scope than what we talked about today. And again, appreciate the opportunity to get in front of you today, and thank you very much.